Am I audible?
Hello.
Yes, ma'am. Am I audible?
Yes.
Yes. Good afternoon, dear participants. Good afternoon, dear participants. I, K.D. Wagmare, lecturer in Civil Engineering Department, welcomes you all on behalf of AISMS Polytechnic for the second session of day 3 of Faculty Development Program sponsored by AICT IST. It's a great pleasure for me to introduce such a dynamic personality that is our next session expert, Dr.B.Siva Soumya, who will talk and share about his experience with GIS and remote sensing. Dr.B.Siva Soumya did her BTech in civil engineering from JNTU Anandpur, Andhra Pradesh. She was second topper in the department. Then she did MTech in water resources and environmental engineering from NIT Warangal, and she was the topper in the department again. After that, she completed her PhD only in the span of 3.5 years from the Indian Institute of Science, Bangalore in December 2008. To more highlight her, I would like to tell you that she was a 729 All India Gate ranker. After completing her PhD, she joined College of Engineering Pune as an assistant professor. After that, she joined MWH Global India Private Limited, Pune as a design engineer in March 2011. In 2014, she joined Dar Al Hancha Private Limited, Pune as an environmental engineer. Now she has been promoted to senior environmental engineer there. She guided many MTech students for their thesis. She has done many technical paper publications in international and national journals and attended many national and international conferences too. Without taking so much time, I know everybody is eager to listen Dr. B. Siva Soumya. Madam, good afternoon. I welcomes you on behalf of AISMS Polytechnic. I am requesting you please start this session. Madam, over to you.
First of all, good afternoon to all. So probably all of you had a lunch break or a small break after session 1. So now, first of all, I would thank AISMS College for giving me this opportunity to share some of my knowledge which I have on remote sensing and remote sensing JS and GPS. It's a great opportunity, despite of having all these practical constraints. We are able to conduct this event, and I have got this chance to be a part with all of you, a big team. So hope I just want to confirm I'm clear and audible, and sir, you can
Yes,
stop me whenever there is any disconnection or any other issues or any other technical issues.
yes, ma'am.
Okay.
Yes, ma'am.
I'll
Voice is
share
clear.
I'll share the presentation and I'll start it.
Yes, ma'am.
So it is clear now? It's visible?
Yes, ma'am.
Okay. Thank you one and all. Start with the remote sensing concepts. So first, let me tell you the main aim to take up this session. We have been doing this surveying. We have multiple techniques of taking the instruments, huge instruments, getting into the field, and then doing multiple ways of getting the surface information, be it to start it from chainage, say long back somewhere in 1996. Graduation, we used to take the chains, the iron chains, which we usually use for buffaloes to tie or something. And we used to take those chains and then get into the field. So our first field survey was the backside of any of our colleges, which is fully of bushes, snakes, everything. Take the chain, go there, have a small team of 3 or 4 of our friends, and then measure the distance. Then again, come back to the college or the hostel room and then measure the length of each chain, note it down, multiply it with the number of chains. That was a tedious process, which we almost took for one experiment. We used to take a day or something to measure a distance between 2 electrical poles. Frankly, it was just a distance between 2 electrical poles on the backyard of the college. Now, if that is the scenario, how are we able to measure the distance between 2 different countries or 2 continents where we are now flying in couple of hours? Like we are able to fly from northeastern part of Asia to the Americans, to the America or to any other continent within few hours. And if we take days to measure the same distance, then how is it possible to get the to work on a global scale? Now, what we are in the current digital world is everything is global. Anyone from any point on earth should be able to reach any other person or should be able to get the information, get the field data. Civil engineering is all about field data, first thing. So get the field data anywhere from any part of the world. Now, in that scenario, when the job of measurement or actual field testing was tedious and cumbersome, this concept of remote sensing or using the satellite data has come into picture. So earlier, the satellite data was just used to estimate whether you will get a rain today or not, or whether you will have a monsoon in time, or whether there is any delay in monsoon, something like that related to mostly up to climate. Or the sensor or the satellite information was limited up to the sky. It was not beyond the sky, and the information reached the earth only, I would say, in the recent era, sometime in 1990s and 2000. After 2000, I would believe this subject or the topic has picked up, or it has got its importance, and we started using it practically and in a more technical way, in a more innovative way. So now, what it is all about remote sensing. Remote, we know, we daily play with the TV remote, and many other things are remote. So what is the concept behind it? What is the basic science behind that? What all principles are there in this remote sensing? And then what are the extension of this basic concept remote sensing is GIS and GPS. GIS will be having a complete detailed session probably on, I think, day 5. And so I would limit my session up to the remote sensing and the GPS application for civil engineering. So my session would comprise of these 5 elements. First, I would highlight on the basics of remote sensing system, the multi-concepts, ideal and remote. What is an ideal RSS should be, so we will call it as RSS, remote sensing system, in brief. Okay. So what is an ideal RSS, but what actually we have in the real scenario? Then we will get into basic physics, that is the spectrum, spectrum. Here we have little physics and little technical stuff. Then we get on to the interaction mechanism and the formation. How is the data acquired from this? In RSS, we have multiple steps. So how is the data acquired as a part of this RSS? Okay, once we get the data, how are we going to analyze it? That is the data analysis section where we will look into it. Finally, after the data is obtained, how are we going to implement or apply it specifically to the civil engineering? See, many engineering sectors come into play when this RSS, in relation with RSS. So we have electronics engineers who deal with the setting up the instruments which can capture the data. Then we have the electrical engineers, and we have many other sectors. But who are the core data users, especially related to RSS and GPS system? It is we. Like we civil engineers need this RSS data for each and every analysis or for each and every sector of civil engineering. That I'll focus it in that section, like how we'll be using it, like how many multiple users or subsections of civil engineering can use this information. Then we will highlight on the global positioning system, what it is all about, how in this Google Maps and GPS on our mobiles. I know most of us have the idea of it because we are already in this digital world. We are using the GPS system when we travel from one place to another. We always have GPSs in our four-wheelers or on mobiles. But how does it run? What is the basic concept that lies behind this GPS? How is the data reaching our mobile? That is what I would like to highlight on in the last session. So to start with, remote sensing. Now, I would get back again to the TV remote. So the remote sensing means a scientific definition is the science of obtaining information about an object, area, or any phenomenon or anything which is located remotely. And if you are capturing the information of it without being in physical contact with it, then it is called a remote sensing. So that is what we do when we edit our TV remote. We sit somewhere in the sofa and in one edge of the hall and try to control the channels or control the volume and other stuff of the TV without being actually touching the TV. We don't get into earlier in our, like sometimes in 80s and 70s, it was that scenario. There was nothing called remote at that time. If you have to increase the volume, go to the TV, then press the button of increase volume. But that is not the scenario now. So there is a mechanism where you can do the things without being in actual contact with the object whose information you want to either edit it, whose information you want to gather it, whose information or pictures you want to collect, or you want to work on it. So in that scenario, we use what is called this remote sensing. So, and typically even before TV, this same remote sensing concept, what we are doing is reading a book. Now I am sitting remotely at some other place, looking at my PPT, and all the audience or all the faculty members are not in contact or neither in contact with me, in physical contact with me, and not with my presentation also. So all of you are sitting at different locations, remotely accessing my presentation or remotely listening to me. So we have actually created a RSS system in this presentation itself. Now, what this RSS system actually has, what are the advantages of it? Advantages is we can have a region survey, or we can get the picture of a larger area than the actual image I want. So I can cover a larger area. If I want only one book, I have to go and physically get it. But if I want the information of the content present in a library, then I can do it remotely. So I don't have to go and get each of the thousands of books from that. So that is what the advantage of RSS. Then easy data acquisition, especially in inaccessible areas. So sitting in Pune, we actually, being a consultant, we work on the site data of Africa or the islands of Western Africa, islands of Eastern Africa. We are not going there in physical. We are accessing the information of it through the satellite images or through the RSS data, through GIS, through GPS information. We actually get even the amount of soil layer present on the top of it, or top of an island in the coast, and how much is the high tide, the tide that has encroached the island. That data we can get it sitting in Pune. So that is what one of the advantages of getting the information of inaccessible areas. Next, a single image can be used by multiple users. That I would explain later. Then color composites and all, 3D analysis is also possible. So again, back into these inaccessible areas, I can know the height of the mountains, depth of the river, depth of the streams, the culvert depth, and much more information sitting here in a remote, far away from the actual site. Faster processing of the digital image is possible using this computer or digital system. Now, there are certain disadvantages or limitations system. Those are the data analysis is technical, so we need expertise in this field who can actually process the data which satellite has been giving it for years. We have the satellites in place, we have the data being transferred in place for years together, and now why we have to learn this subject is because we have multiple vacancies and we have shortage of the people who are technically experts in handling this RS data. That is where we are looking for. Another disadvantage is we need a high-end software, but okay, this was one of the disadvantages earlier, but now technically we have developed to process the data in a much higher accurate level, higher accuracy. Then it should be one thing still we have is it has to be supported with field investigation. But yes, now the field investigation data that we are dependent when we are using RSS is not only 5 to 10%. And in this scenario, we don't need an expert to go into the field and do the data, but we usually send, or usually the local villages can also just verify the field information, because we have got the 90% of the data. We a small local villager to go and check whether the river exists. The map that we have received for an African island tells us the height of the hill, the depth of the river, everything. But what we need to just ensure that it is the river and it is not some other drainage canal or some other sewage canal being built artificially. Is it a natural stream or is it a sewage canal? That is what we want to verify. That any villager can go and tell, yes, it is, or any localer who resides in that area can give us that information. This information we label it as a field reconnaissance or a field authentication from a field surveyor or a support of field data. So that is the only minimum 5 to 10% of the information that we need as an assistance to the RSS. Now, what are the different types of RSS information we receive? That I would say multispectral, multi-temporal, multi-stage, multi-station, multipolarization, enhancement, disciplinary, and thematic. Now, spectral, multispectral in the sense we receive data from different spectrums of a radiation. So that would be more clear probably once I speak of the EMR, VGR, the radiations and all. But for now, just remember, we receive the data from multiple wavelengths, multiple radiations. That is multiple bands. So I get information in one band of radiation and second band of the next radiation, and I receive a wide range of data from wide range of bands of spectrum or the sun's rays in a crude language. Temporal, multi-date is okay, is self-explanatory. We can receive the information of a particular site over different time dates. So if some flood is occurring, I can have the pictures at every 5 minutes or at every second, and that is the temporal resolution or the date or temporal data that we receive. So we can simply like ask the satellite to produce the data at the resolution what we need, at the temporal resolution that what we want. Multi-stage is again related to the pictorial resolution, or I would say the color graph. Multi-station is yes. So if I look at this laptop directly face to face, that this is one station. If I look at the same screen at an aligned position somewhere at 30-40 degrees from the straight, that is the station 2. And if same wave on either side, station 3. So I can have multiple the satellites or the image capturing stations at multiple points in the atmosphere, and that data is being captured again by multiple stations or receivers on the earth, and they all give us the information of one particular site or at one particular point. That is where we call it as multi-station. Multipolarization is again linked with the radiation, that is the spectral band, and multi-enhancement. Now, enhancement is if I get a crude data, how can I enhance it to multiple use? Say somebody wants it at a resolution of 5, somebody wants the details of only 100 by 100 meters. So if I'm happy if I know what it is present on a 100-meter area. Okay, that is one level of enhancement. If the second user wants it at 50 meter by 50 meters, no, I should know the details of the land at every 10-meter distance. Then it is multi-enhancement. So again, I have to enhance it up to 10-meter resolution scenario. Like that, based upon the need of the user, the RSS data is being enhanced from a crude level to a much finer level. Third, next is multidisciplinary. Multidisciplinary, as I said, a hydrologist will use an RSS information in one way, surveyor will use it in one way, a groundwater professional will use it in a different way, GIS expert will use it in a different way. Similarly, structural engineer would focus on the buildings, or a hydraulics engineer would focus on the bridges and other stuff. Then a geotech engineer would look at on the land use or the soil types, like that. So multidisciplinary. Then again, multi-thematic is again linked to the spectral way, spectra and polarization aspect of the data. So what is an ideal RSS, and how we are deviating despite of having this high technology? Ideally, in an RSS, first of all, an RSS has all these systems. It should have a source which emits a radiation. It has an atmosphere through which the energy passes. Next, it has an energy matter interaction, that is a surface where this radiation hits. Next, a sensor which captures this hit radiation. The energy radiation which hits the surface again rebounds back like a ball. We are hit to the ground and it rebounds back. So the rebound radiation is being captured by a sensor. Then the sensor again gives us a data which is to be processed. The data being processed for multiple users is the same data has to be used by the multiple users. Now these are the different elements of an RSS. In these elements, ideally how it should be, you should get a source of energy uniform continuously. Day, be it an afternoon, be it an evening or a midnight, any part of the day, any part of the year, on any part of the earth, you should get a uniform data. The picture should be the same. Ideally, the picture of, say, the college should be the same whether I take it in the midnight or whether I take it in the mid-afternoon. That should be an ideal RS system. The atmosphere should be non-interfering. Every sunlight or every quantum of energy or every molecule being emitted by the source should reach the earth. It should not get absorbed by the atmosphere. The atmosphere should not interfere with the environment. I don't like any noise or any disturbance. It should be non-interfering. Then this molecule, each and every molecule of the radiation should be unique. It should be invariant to the surface. Means even if I have a hill or a sea or a land or a road or any other building, the molecule should react in the same way. It should be unique. It should not get distracted on reaching the earth or on interacting with the surface. That is the ideal RS system. Next, I need a super sensor. A super sensor which can capture all the bundles of data. That should be a part of the RS. The data processing. Now, after all these molecules have interacted and reached the sensor, the data that I receive should be continuous, real time, instantaneous. It should get updated within fraction of seconds. Then the data again, even if it gets interpreted or even if it gets updated in a fraction of a second, it should be readily interpretable. There should be no expert. We should not need any individual for it to be interpreted or for it to be enhanced. Why do we need a manpower? Directly the satellite should give me an image the way I want, the way the user wants. If I want to focus only on rivers, I should get only the river data, like that. And the image should be in such a highly interpretable format that everyone should be able to read it. Any layman, any individual user should get the information what he wants. Is that the scenario, or is that the level of RSS that we have now? No, we have some deviations from this ideal RS system. The deviations are, I have a non-uniform energy source because I have a morning, I have a midday, and I have an evening and a midnight. Midnight, there is no energy source or the direct solar source. Midday, I have the huge bulk of data or huge bulk of quantum of energy. And this quantum of energy varies in morning and evening. Again, morning, evening, midday is not same all over the world. It varies from continent to continent. So I have a non-uniform source which is variable from space and time. Again, I have an atmosphere which absorbs this quantum of energy. Say if I have one complete ball of energy being emitted by the source, I reach only 80% of it, or that absorbs 20% of it. Then once it reaches different materials with spectral and with different materials with different similarities and different differences, and they absorb, like hills absorb the radiation to certain extent, the vegetation absorbs in a different way, then the other bodies absorb it in a different way. Similarly, the sensor, so there is no unique sensor till now developed which can capture all the wavelengths and again differentiate it on the spot. There is nothing like that super sensor. So we have to put one particular sensor for a wavelength, for each of the wavelength. The sensors have to be unique. They cannot read the whole bandwidth at one go and then give, and again they cannot disperse the data in the same way. Then data processing now, earlier it was manual and now it is all digital mode. So we have multiple softwares and multiple techniques also of processing this data. Then this is where I think some scientific teams of ISRO helps us. So as soon as they receive the data, a part of it is being processed at their end. Then we have the data being processed by the experts. That's what I was saying. We have the expertise teams processing this information from multiple. Then we don't have any essay, and we don't have a single picture format which can be used by all. So every user has to develop the raw data as per his or her needs, and then use the information which is being given it after processing. So what is the current scenario? The real RS scenario is repetitive observations of the same area is required in the present RS system. So I hope if the technology develops, we might reach just nearer to this ideal RS system. But in current scenario, we are in the real RS system where repetitive images or repetitive observations have to be taken of the same site to get the confirmation of the actual field scenario. Next, let's get into the, after listening to the basic RSS, like basic concepts of the RSS, we first focus on the radiation. What is all this radiation about? Spectrum. Now, these here, what for some few more slides, say 2, 3, 4, few slides after this, we will get into the physics of the radiation or physics of the quantum photons and all that stuff. Radiation or any electromagnetic energy is defined in terms of its wavelength and frequency. Now, what is wavelength?
Excuse me, madam. Excuse me, madam. Hello. I cannot hear your voice, madam. Soumya, madam.
Hello.
Excuse me, madam. Can you hear me?
Hello.
Huh. Yes, ma'am.
Yes, okay, is it visible now? So audible now?
Yes, ma'am. Yes.
हाँ, ठीक है. From where it got disconnected? Hello.
Hello, madam.
हाँ, कौन से slide से disconnect हुआ है?
Actually, your PPT is not visible right now.
I'll share it again now.
Okay,
I have
ma'am.
stopped sharing it. I'll share it, but just let me know where it was, where it had stopped.
Electromagnetic wavelength.
Okay. Is this?
Yes, madam. Yes.
Okay. So we'll start with the basic principles. Here, so I think the crust and troughs. Okay. What does the any radiation would propagate like this in a sinusoidal waveform with two crusts and two troughs. Now the wavelength is the distance between two successive crusts and two successive troughs, which are the lower peaks, and crusts are the upper peaks. That is, the wavelength will remain the same whether we measure it with respect to the crusts or the troughs. Now that we call it as lambda. Lambda, and the frequency is the nu. This nu is the number of peaks or the number of peaks that occur in a unit time, is the frequency of the radiation. Like how many photons will pass through 1 second. Photons of this light or the molecules of this light will pass through a particular this wavelength distance in 1 second. The number that will be the, or how many crusts will pass through, that is given by the frequency. Now c is the speed of the light, which is 3 into 10 power 8 meter per second. Now, relation between these radiations, the speed with which the radiation propagates, the distance between the crusts and the frequency is c is lambda nu. Speed of light is the wavelength times the frequency of the radiation. What is the energy that passes, or how do we quantify how much of the radiation has passed through, or how much of the radiation that we're going to receive on the earth, or how much is being emitted by the source, like that. So this quantum of energy, this particular word or this set of words will be like I should say it's the core of RS, because everywhere what we measure is this quantum of energy that is being emitted by each individual element of RSS, be it a source, be it an emitter, be it a surface, be it a sensor, everything. So quantum of energy being received, Q, is h nu, h being Planck's constant, which is given as 6.6 into 10 power minus 34 joule per second. And nu, again I take the first equation, that is c is equal to lambda nu. If I substitute nu with respect to speed of the light, what I get is hc by lambda. Hc by lambda is an equation which gives us the quantum of the energy. Relates the Planck's constant, the speed of the light, with respect to the wavelength of the radiation. Now our focus in RS will be the relation between lambda and Q. Lambda is inversely proportional to Q. That means lower the wavelength or lower the wavelength, the energy would be will be higher. And if the wavelength is like long, lambda value is small, is very long, or the longer the wavelength, lower will be the energy. So how is it related? We'll see as we proceed. Electromagnetic energy. Now, that is what I was talking about. Longer wavelength and shorter wavelength. Vibration of the energy is perpendicular to the propagation. That is what it was clear. The direction of propagation and the electric field, magnetic field, all the three are mutually perpendicular. So we have X, Y, Z three-dimensional concept in with respect to in this energy propagation principle. So it is the energy, the direction with which it propagates is perpendicular to the vibration of the energy. Easier to measure short wavelengths. That is when because it will have a high quantum of energy and you can detect it easily if it is a shorter wavelength. The longer wavelength has a lower energy, so you need a high resolution sensor or a high-end instrument to capture this lower wavelength. Gamma rays are most energetic and radio waves are the least energetic. So, and best main thing that we have to identify is clear-cut division between these spectral regions. Like WebGR, when we see WebGR, we have the range from violet rays to the red rays, but we don't have anything clear like, okay, from A to B it is violet, B to C it is indigo, then I have like orange, green. There is nothing like that one particular boundary wall sort of thing between the radiations. It just transforms from one wavelength to the another, and the energy it emits or the energy that the photons contain vary from one level to the another level. Shorter wavelength, which will have the blue radiations or the violet radiations, and the longer wavelengths will have the they correspond to the red end of the WebGR spectrum, and they have low energy, low frequency. The violet and blue end will have high energy, high frequency. So this, when I put it on a complete spectrum or the spectrum of the rays that we have identified so far, what we see now, the white color, we all know like rainbow colors, all the colors of rainbow merge into white, and that is why we see the clear sky as a white. Now that is a very, very small, narrow range of the entire spectrum that you look at. Spectrum starts with A here is 8 degrees, that is angstrom. 0.03 angstroms to 300 kilometers of length, we have the spectrum or the range of radiations that our satellites or the data that we receive. And of course, our satellites are capable of capturing these ranges. That is how we have identified that identified the speed of these ranges or the wavelengths of these radiations. So we started with from 0.03 angstrom. Angstrom is 10 power minus 20 meters to minus 10 meters to 300 kilometers. So first, the gamma rays are being identified at this lowest wavelength. And since again we repeat, the lower wavelength means what we have, the lower energy. So these gamma rays, it is very difficult to capture, so might not be suitable for RS. Similarly, X-rays, they also have a very low wavelength, so they are not suitable to they are not suitable for RS purpose. But these X-rays we are using to read the internal damages caused to a human body. UV rays, they are harmful, but they are being used for certain purposes. Then 0.4 to 0.7 meters, this is our rainbow range or the visible light or the main visible range where we do most of the experiments, and then we extrapolate or we try to use the similar concept for the rest of the EMR spectrum. So this entire range, I would call it as electromagnetic spectrum or EMR spectrum. Now I would focus on the RS bit of the spectrum. RS bit would start somewhere from this visible range, 0.4 meters. it would extend up to 0.7 is the VR. Then I have the infrared. So I capture these infrared rays. We have satellites or we have certain sensors which give us the pictures completely in IR bandwidth only. So in this IR bandwidth, we get the data, and I'll show you. I can show in one of the slides where we have the images all in different shades of red. That is where we have captured the data in infrared bandwidth. Then we have the microwave bandwidth somewhere between 0.3 centimeters to 3 meters of wavelength, radiation with this wavelength. In the same microwave bandwidth, we have the radar bandwidth. Then the radio bands, all our radios, FM radios work in this range of wavelength. That is 3 centimeters to around 30 kilometers. Then what we see below, this is again the frequency scale in comparison to the wavelength. This can be easily derived with respect to that equation. C is equal to lambda nu. After this what are these black patches we are observing? These are the atmospheric attenuation, or the zone where atmosphere absorbs the radiation. Here where the real RSS has come into picture. What we were talking, the atmosphere should not absorb anything, but that is not the scenario. All the lower wavelength radiations are being absorbed by the atmosphere, and we are able to receive only a very nominal fraction of the radiation. That is why we have low quantum of energy, because it is being absorbed. Nothing reaches the Earth's surface. And then next, but when you see on the right side of the visible spectrum, you have certain range of quantum being received by the Earth. So we have atmospheric attenuation is lesser on the larger wavelength bandwidth, or when the radiation is of larger wavelength. Now, these radiations, when they reach, what all types of phenomenon or the interaction mechanisms that occur when it passes through the atmosphere? Either they have, these are different molecular or moleculochemical reactions that occur in the atmosphere when these photons pass through. Either they dissociate, they create ionization, and they get heated because heating occurs in this larger bandwidth of range radiation. And there are electron shifts in the visible range spectrum. Then we have molecular vibrations in this infrared bandwidth. Then we have rain and fog attenuation. So sometimes the rain and fog also absorb certain radiation, that is mainly the infrared and microwave. So microwave radiations would not work if it is in a cloudy zone. Similarly, we have noise and astronomical attenuations in this radar range. So these absorptions have to be corrected for once we receive any data. After looking at the basic principles of these or the basic physics of the photon or the quantum energy, we will get back, we have received some quantum or volume of energy. What we have to do it means, okay, there is a receiver and the source is a continuous source, that is a solar energy. For this continuous solar energy, we have got a receptor or a receiver on the Earth which has captured the energy in this say VIBGRs in this normal white light bandwidth and in the IR bandwidth. Now what we have to do with these radiations? We have got some energy, we have got the light, we have got a continuous light being emitted by the sun, and what I have to do with this quantum energy? That is where the interaction mechanism has to be studied. How much of the atmospheric attenuation is going on? What is the sort of image that we are giving? What are these interaction mechanisms? Those are studied in different ways, like in a step-by-step procedure. Now, first we look at the energy source, the solar energy, how it is being emitted, then how it would propagate the energy through the atmosphere. Since I know the basic concept of the EMR spectrum, so the wavelength and the equations linked to this photon energy generation, I would like to focus on the propagation of the energy through the atmosphere. Then how does these photons or the energy interacts with the Earth's surface feature? So there are certain things in this here. Now, first the energy source, low energy content of long wavelength. So what we saw is long wavelengths have lower energy, the same EMR, the same wavelength, right? Okay. Since it has got a lower energy, it has to cover a larger area to get a detectable signal or to get a detectable image. So we'll say signal or an image for your perception. So sun is the source, and any source other than sun or any heating object or any hot object which has got its temperature more than 0 degree Kelvin will emit the EMR radiation because of the molecular reactions. So any object which is heated up to beyond this 0 degree Kelvin can give us the EMR radiation, which we can capture it for the RSS purpose. EMR is a function of the surface temperature, like the total energy being emitted. Since it is a function of the temperature, or this 0 degree Kelvin is the threshold, this radiation is given by a Stephen Boltzmann's law or a black body concept. That is, ideally a black body doesn't absorb anything. It has zero absorbance. It totally radiates 100% of the radiation outward by a relation given as the constant sigma into 4 times the temperature. So if I have some, if the temperature is in absolute Kelvin, temperature is in Kelvin of the emitting surface, the constant being 5.66 in 10 power minus 8 watt per meter square per temperature per 4 Kelvin per 4, then the amount of energy being emitted. So the photon has reached the black body, or this is applicable for the source also. What is the temperature of the sun or energy emitting source? That if we know the T value, then we can compute the amount of photon or the amount of total energy being emitted by that particular source. So a black body is ideally radiator, but sun it's not a complete black body. So we say any black body would emit this much of energy at this temperature, totally absorbs and re-emits all the energy incident on it. So if I get some Q quantum of energy from the source, then if it is being received by a black body, it would emit 100% of it back to the satellite or back to the sensor for it to receive it. High temperature contributes to the shorter wavelength. Again, here we are trying to link the temperature of the emitting body with the wavelength of the radiation being received. So we have peak radiation at 400 degrees centigrade. So this is what the total radiant exitance curves. So what I have done now, for different temperatures, a graph is plotted between the radiant energy being emitted versus the wavelength, which is in micrometers, for different emitting surfaces which are being identified as at a particular temperature. Say one radiant emitting body is at 200 degree Kelvin, another is at 300. Like that, I've taken different radiant energy hot bodies at different temperatures, and then we have measured the radiation being emitted. What is the total amount of radiation being emitted at different wavelengths, and what is the wavelength of that particular radiation? So these graphs indicate the black body which has a surface of 6000 degree Kelvin temperature would emit the peak energy. So that would emit it. Again, it will not emit the peak energy all through the EMR spectrum, all through its existence, and it is not a straight line graph that it will emit this particular amount of energy, 10 power 8 watts of energy all along the entire EMR spectrum. No, it's again a bell curve, or it's again a normal distribution curve. So this would emit a peak energy at 6000 Kelvin. At this 6000 Kelvin, considering this black body as the highest emittance or the threshold value or a symbolic static value, we started comparing the amount of radiation being emitted by other bodies at different temperatures. See, now at the sun's temperature, it is 6000 degree Kelvin is the sun's surface temperature, emitting 10 power 8 watts. When we go for a lamp, that is the incandescent lamp of our home, that again works at 3000, that has the peak temperature of 3000 Kelvin, but it will not emit the highest energy at the same wavelength. Means it will not emit a maximum volume of energy at this wavelength only. It is not that, okay, I have got a sensor which will capture the data at 0.5 micrometer wavelength. That will work well when it is a sun's temperature, but it will not work well if I am putting the same sensor inside my house for an incandescent lamp, because the peak has shifted. The peak radiation has shifted to a next wavelength, which is between 1 to 2 micrometer. So I should be careful while defining a sensor, or the amount of radiation that is being accepted by a sensor is not the same for all wavelengths, for all temperatures. And say for one particular temperature, it is not that all the bodies at that particular temperature will give us the radiation in a single range. No. So if one gives at 6000 degrees, then the moment the source has changed, even if it has got the same highest temperature also, the range of wavelength being captured will be different. It will be between 1 to 2 for lamp. Similarly, for the Earth's temperature, so Earth's temperature maximum would be 300 Kelvin. So this 300 Kelvin will not be captured at 1 micrometer wavelength. Rather, it will have its peak only at 10 micrometer wavelength. So a radiation of 10 micrometer wavelength will be captured very well, because that has the peak energy at the Earth's surface temperature. This shift, how much is the shift in this wavelength, is given by Wein's displacement law, which is the area by temperature, A by T. So based upon the amount of this solar energy, its temperature, the amount of energy being emitted by the source, that was this concept, the total radiant excitancy, or the energy being emitted. Now, I would say the total energy is at this radiant emittance is the value. Now, what is the quantum of energy that I have received? Quantum of energy I have received is the area under this total graph, this bell curve. The total area, say around like this 6000 for Earth. If you take 300 degree Kelvin, ranging from say around 4 micrometer length to 55 micrometer length. So the area covered by this particular graph is the total energy being emitted by the Earth's surface at this particular temperature, at 300 degree Kelvin temperature. This energy now will propagate through the atmosphere. Again, getting back to ideal versus real RSS. Once the energy propagates through the atmosphere, all the radiation detected by the sensor passes through so we don't have any sensor right next to the sun, so that there won't be any atmospheric absorption or total energy will be received by sensor. I cannot have like that particular sensor. So there's certain distance between the sensor and the source of energy where we have the losses. Why do we have these losses? Because energy being sent is either scattered or absorbed. So I would say it has absorption or a scattering phenomenon of the atmosphere, which reduces the total quantum of energy being emitted by a source or a solar energy, or by the sun. Now, the scattering is unpredictable diffusion or redirection of the radiation by particles in the atmosphere. Why does the atmosphere scatter the data? Why can't it send the one single line of ray directly to the Earth? Because you have got multiple dust particles, you have got the gases, we have got the rain droplets, haze, and the length, the distance, the thousands of kilometers between the source and the receptor surface or the Earth surface. gives or it weakens the radiation because of the length it propagates, and because of this all more than the disturbances caused by all these particles inside the atmosphere. It depends on the particles, gases present, and distance traveled by the radiation. So distance, I would say, is not a controlling factor, because ideally the radiation should travel with the same energy for thousands of kilometers for indefinite distance. Now, all these hindrances will cause the scatter or the absorption of the radiation. How do that? Now we are lucky enough to quantify this scatter also. Quantifying this scatter in the sense, you have what is the diameter of the particle to which this radiation is hitting. If the diameter of the particle is less than the wavelength of the interaction or wavelength of the input radiation, then it is called Relic scatter. Relic scatter is proportional, or the effect of scatter is Relic scatter by default. Please remember, if the diameter of the particle is less than the wavelength, means the photon of the radiation or the wavelength length of the radiation is much larger than the particle size of the dust or the gas or anything, then you have the Relic scatter. Scatter is proportional in an inverse way with 4 times fourth power of the lambda. It is not 4 times, it's lambda power 4. Shorter wavelengths always scatter by this mechanism. Okay, blue sky is a manifest. Now, why blue sky is a manifest of this Relic scatter? Or because of this, otherwise it would have appeared black. Means we have different wavelengths. Because of the radiation or the Vidya radiation being scattered, we are able to see the combination of all the colors of the Vidya, and we are getting this blue sky or the white sky. If this scattering would not have occurred, then especially during the night, why the nights are black? The nights are black because the radiation that is being received, radiation first of all is being received is nominal, is very less, and there is not sufficient radiation for it to being emitted, and it would appear as a black atmosphere. So here, because of these particles, the sky would appear because of this particular Relic scatter, and because of the particles present in the atmosphere, we are able to see the blue sky. Shorter the lambda value, then now what if the diameter of the particle is equal to the wavelength? So if I have some dust particles which are equivalent to 0.4 micrometer of the 0.4 micrometers is the wavelength of the Vidya, this one 0.4 to 0.7. Now what if I have a diameter of a particle which is equal to this 0.4? Then it would get subjected to my scatter. That is, longer wavelengths will scatter. The type of scatter that it is subject to is defined as a my scatter. Then if the diameter of the dust particles, or if say these are more applicable for the different types of gases which have smaller diameters. Now I have these dust particles and other pollution particles which are being emitted into the atmosphere. These the sizes of these particles are much greater than the wavelength being interacting. In that case, you have non-selective scatter. That is, water droplets cause such scatter. So the water droplets of the atmosphere, raindrops, cause this non-selective scatter. Non-selective scatter will be with respect to the wavelength. Equal quantities of blue, green, and multiple colors get blue, green, and red. Equal quantities get scattered, and that is why we have sky appearing as white. So white color of the sky is because of the non-selective scatter of the radiation, and blue sky is because of the Relic scatter of the radiation. So here we have a picture. Now what we are talking about is this radiation which is passing through the atmosphere. So ideal atmosphere should give the same width of arrow here at the satellite also. But since in a real RSS system, we have the portion of it being absorbed, we have a portion of it being absorbed by the atmosphere in
on both the ways. So when it travels from source to earth, it is getting absorbed. Again from surface to satellite, again it is getting absorbed. So on both the ways, in both the directions or two paths, it is being absorbed, and that is what we are talking about. We are talking about the absorption in this transit, or the dotted arrow mark, which is being represented. So after that, then the absorption. So scattering, and another type of absorption is the loss of energy because of these atmospheric constituents. Loss of energy is like water vapor, CO2, and ozone are the major absorber. So I think we saw this picture earlier also in the EMR spectrum. So there I was talking about atmospheric attenuation. Atmospheric attenuation is the amount of energy being absorbed or energy being blocked. That is this gray portion or the black portion in the previous slide. So this is the quantum of energy being absorbed by the atmosphere, and the white portion is the transmissive wavelength or the window, atmospheric window, through which we can receive the energy, or only this quantum of energy is being received by the sensors, or what I call it in a common language is I can see only through these atmospheric windows. The rest of the window is blocked for me. It is black for me. So it is not being detected by any sensor, especially the attenuation or the blocked portion. Only the windows are window zones of the wavelength, and window length, percentage of transmission is being detected by the sensors. This is where the actual reduction in the energy occurs. So like infrared and UV, visible and infrared. Apart from UV, mainly visible has 100% transmission. Visible range of light is not being blocked by the atmosphere. Most of it is being transmitted. So we are able to capture it. And especially, and another sector is this infrared. Infrared also we can capture it. So mostly we focus on these for that reason, like spectral scanners, thermal scanners, all work on this wavelength range and this transmission zone to capture the energy. Energy interaction. Now this is all the theory part. So what I would say next, after being absorbed by the atmosphere, whatever it is allowing through the window to reach the Earth's surface, again it is a portion of it. It interacts with the Earth's surface. So what is the amount being reflected by the Earth? Is it same as that being received by the Earth? No. So reflected energy is the amount incident on the Earth's surface, or the incident energy, total incident energy, minus Earth atmosphere absorbed energy plus the Earth's surface absorbed energy, energy absorbed by the Earth's surface, and vegetation, water, or anything. Any feature on the Earth absorbs certain energy. So the incident energy minus this absorbed energy minus the transmitted energy. So if I take out this bracket, it becomes I minus A minus T is the reflected energy which is received by the satellite. Now, the remote sensing operates in the wavelength bands in which reflected energy is predominant. So what we saw earlier was WebGR range had 100% transmittance. And again, the infrared has the highest transmission. At the same time, even if it has the highest transmission, highest reflectance also. Proportion of reflected energy varies from Earth's surface to surface. Why? Because this is playing the role. Absorbed energy component plays the key role. With a given feature type, those proportions will vary at different wavelengths. Spectral reflectance is what we call spectral reflectance is the ratio or the percentage which we define to quantify the amount of energy being reflected by the surface to the total incident energy. Means I by R. The incident energy is the total incident energy. And what is the reflected? How much of fraction of it is being reflected? This percentage is called spectral reflectance, or Lambertian reflection or rho lambda. Rho lambda is energy being reflected upon or by energy being incident on the Earth's surface. Spectral reflectances. So we have different spectral reflectance percentages for different types of features on the Earth. If I take it this percentage, what we have deciduous trees, coniferous trees, again all the unique feature of the vegetation or nature is that every leaf has a unique reflectance power. The percentage might remain the same, but it has a different way of reflecting the energy. That is why even in RS or even in satellite images, we are able to distinctly see the different types of vegetation. So one of the applications of RS is to identify the types of vegetation also. For land use land cover identification also, we use this RS images. We use this RS system. Why? Because this is the reason. Reflectance of pine trees is low. Reflectance of deciduous trees or maples is high. Similarly, top portion of vegetation will reflect in one way. The canopy vegetation will reflect in another way. The underground vegetation here will reflect in a different way. Similarly, the infrared bark of a tree will reflect more of the infrared, the another radiation, the long wavelength. Small bushes will reflect infrared radiation more. So based on the different types of wavelengths these particular surfaces reflect or emit, we can distinguish the type of the vegetation. This principle is used to identify whether it is a park or a natural park, artificial park, forest, or a field, farming field, what it is. So this distinction, using remote sensing images, we are able to identify these different features because of this reflectance property. Now, this reflectance property, when I compare it for, see, again for natural graph and turf. Natural graph has high reflectance after certain wavelength, but artificial turf reflectance in the infrared zone is less. So this is, so if you can take the images between this band, in this or infrared wavelength, you can distinguish between the natural grass and the artificial turf. So one with the natural grass will have highest reflectance and will give us a clear picture. One which is an artificial turf or our artificial grass will not reflect much. Similarly, if I look at the reflectance curves of the soil, water, so I have different curves for this. The valleys in the visible range between these two valleys or these two main valleys at 0.4 micrometers and 0.6 are called chlorophyll absorption band. So it is these valleys which are being captured to identify the vegetations. Now the same, that is why we identify them uniquely as a chlorophyll absorption bands. Now all this reflectance is because of the presence of the chlorophyll in the leaves. So that is back to 6th class, 7th class science. Okay. High reflectance in NIR range is useful in identification of different species. Large differences in spectral patterns in visible band and significant difference in near red and middle infrared. So this differences in infrared band is being captured for identifying different types of vegetation, soil, like that. Useful for vegetation condition monitoring also. Then beyond 1.3 here, more reflectance or absorption with little transmission. Then here for the water I would say is this dashed line. Water has water absorption bands like how we had chlorophyll band in 0.4, 0.7 micrometers. So water absorption bands are more clear or distinguishable in middle infrared bandwidth. So that is at 1.4, 1.9 and 2.7 micrometers. So these three peaks, 1.4, 1.9 and this 2.7 peak, see these valleys, not the peaks. These valleys indicate the water absorption bands, while these two indicate the chlorophyll absorption bands. Example of IR band. So visible portion, everything was looking green. Fresh park, trees, everything is green. Now, when I go for a IR image, So all this natural vegetation was reflecting it maximum, the reflectance of the vegetation in infrared bandwidth or infrared radiation was maximum. So I got the red color. But the artificial turf of the stadium, that is not being reflected in the infrared bandwidth. That is why I saw it as a greenish or black color. So this color distinction will immediately help me in identifying the artificial vegetation versus the natural vegetation. This is how being images here we have the example of multi-level spectra or multi-spectra analysis. After the earth has been reaching the earth's surface, see, the radiation has reached the earth's surface, the interactions have occurred, transmission and reflectance curves we have seen. Now what happens once the ball has hit the ground or the radiation has hit the earth's surface, it has to bounce back. So that is the retransmission of energy to the atmosphere. Sensing systems, how much do they sense? What are different sensing systems we use to catch this bouncing ball? Okay, that is what the next topic is. This is again more of theory, because when we go into in-depth, we can do practical analysis or examples on this retransmission and mathematical problems on this. But I think that is for quite a higher level. Spectral emittance is distinguishable for 300 micrometer wavelength. Response patterns observed by remote sensing are quantitative and not spatiotemporal effects are response patterns. Atmosphere reduces the, just give me a break. Atmosphere reduces eliminates as a reflector, scattering, extraneous path radiance and signal. So we have a equation here that is total radiance emitted by the Earth's surface is given as reflectance of the object, the percentages that we were looking at, the graphs, percentages that we were looking at so far, that rho into E, incoming energy radiance, the transmission T, and the path radiance. LP is the path radiance from the atmosphere, and this path radiance is of the atmosphere, from the atmosphere, and not for the Earth. So this total spectral radiance being calculated is measured by the sensor, and that radiance value is used for the design of particular sensor. Now, what are different types of sensors we have? We have one active sensor, one passive sensor. What is active sensor? The sensor should have its own energy. It should emit its energy and recapture it. Passive sensor is, it should depend on the source or on a different source. The passive sensors cannot emit any energy. They just capture it. They just know how to take it. They don't know how to give it or reflect it. So these, in case of passive sensors, we use the solar energy as the source. In case of active sensors, we can capture, that is, these active sensors are helpful, especially when we capture the data of night or places which are having night. So there what happens, these active sensors, they will emit their own energy, take a, it's something like flash of our camera. It will put its own energy, take the picture, and it will give us the clear picture despite of being zero light or despite of being a night or being dark. Now, camera is active on the daylight, passive when records flash. It is active on the same example which I gave. Flashlight or flash camera is a active sensor, and normal camera being functional during the daytime is passive. Criteria for selection of the sensors: spectral sensitivity of the sensors available, presence or absence of atmospheric windows in the spectral range, each one is to sense. So they should be the ranges in the range of the wavelength in which a particular sensor can sense it should be defined. Also, we should be knowing the range in which the radiation will be received. After all these atmospheric attenuations, reflectance, absorptions, everything, source magnitude and spectral composition of the energy is available in these ranges. Now, how are these sensors placed? We just cannot, it's not a water bubble that we just flow it and it will go to the atmosphere and give us the data. No, we have certain platforms. That is, olden types was these balloons and aircrafts. So ground observation, the crude way or the simplest way or the old technology was to put it in an air balloon or a parachute, place these sensors, and then they will give us the aerial data or the aerial pictographs. Then we have it in a low level aircrafts. Now, what does this scale mean? Is the height at which each of these sensors capture the data or the pictures. So if it is an aircraft, it is just nearer to the ground. If it is a sensor which is just tied to an light pole or something, we have ground observations. Then next level, slightly above the earth, is aircraft. And if we put these sensors in an aircraft, it will be still high, a little higher above the earth. The one which are the one which give a regional picture of high resolution and which are far away from the earth are these low altitude satellites and high altitude satellites. Low altitude satellites, we call them as sun synchronous. Example is Landsat, Spot, IRS. Developed by IRS, developed by our Indian teams. Then these sun synchronous satellites are called polar satellites because the orbit coincides with the sun. The name itself suggests sun synchronous means they are in sync with the sun. So they always look at the sun. They always look at the sun because they need that quantum of energy from the sun uninterruptedly throughout their operation. So they get one lump sum of the solar energy at all times. That is where they are facing the sun and placed at 300 kilometers distance. Now, what they emit or what they give us pictorial is the shades of the earth, provided the sun being kept as a constant or the sun's energy being kept as a constant, we get the shades of the earth here. Now, the vice versa is geostationary satellite, which are high altitude satellites placed at 1000 to 1300 kilometers. These geostationary satellites are the other way around. They always face the earth. They are earth synchronous. They have low resolution because they are at a very far off distance, and they are placed at an orbit 36,000 kilometers above the equator. So they are always placed at a particular distance from the earth, or they always visit the same means their rotation or their revolution is in sync with rotation of the earth. So they follow the earth's rotation, while sun synchronous follows the movement of the sun. It is not actually the movement of the sun, but they revolve with respect to the sun. So that always face the sun. This is sun synchronous. Geostationary always face the one part of the earth. Now, these different types of sensors, sensing systems or sensors, these are like on an average crude ones. Then we have higher versions of these, okay, or some sensors which can do like multi-purpose, multiple tasks of both the same. Then these sensing systems, they generate the products which is of our use. What is the data that is being sent by these sensors, being an earth geostationary ones, geosatellites, or sun synchronous? Any of these satellites, they give us data either pictorially or photographically. Photographically, whatever data is being sent by the sensor or being generated by the sensor, that we develop it using a chemical reactions on the surface of the light, and a sensitive film is used to get energy variations. This is similar to our X-ray because we take gamma radiations as the input and a film is placed, and this gamma radiation does chemical reactions on the film and produces the X-ray of a human body. So similarly, these sensors, when some sensors which give pictorial image, they have certain reactions on the film on the surface and then give us a picture of it. Now, whether the picture is readily usable or not, it depends from sensor to satellite to satellite. This is simple, inexpensive, and it gives a high degree of spatial and geometrical integrity. Now, why we are not going for this pictograph directly, why we are getting into the electronic version of it? That is because when we want to enhance the data or use the data for multiple users in multiple perspectives, then we need to transform the data. If I get a picture of a field and if I can use it directly, okay, I will adopt only photographical way. I don't have to modify it or work on it or analyze it electronically, or I don't need the digital numbers of it. That is where then if you have to transform it, I go for the pixels or the digital numbers of each of this picture corresponds to. That is, electronic sensor generates the signals corresponding to the variations in the original scenario. Broader spectral say for in the picture it is clear. If it is a pictorial format, you will have like this. Now this is nothing but a array of pixels or a small say some 0.1 by 0.1 meter square has got some data, and mixture or the sequence of this 0.1 by 0.1 meter pixel is what the actual image of. Now what the electronic way of sensing does, it will give us these pictures in terms of numbers. That is the bottommost table. This table here, what happens here, I have some 17, 12, 27 different numbers. Each number corresponds to one pixel, or it is like a hint number showing us about some particular feature. Now what is this hint number? This hint number can only be decoded once we know the input given to a sensor, where the electronics engine is coming to picture. So they decode this language, this pixel language or this digital number language, DN, this array of DNs, and then convert back this electronic data into pictorial form. Now they will play with this numbering system is advantageous because we can play with these DN numbers when we want to transform it into, say, I want a higher resolution picture or a lower resolution pictograph for any type. I can easily transform these DN numbers. That is where I need the electronic data. Now, computational analysis, yes, this is more clear. Say I have got, this is the land feature image. We got of gray, 3 shades of gray. When I look at the electronic version of it, I have got these DN numbers. Now these DN numbers, 200 represents a larger area, say around 5 meters of area on Earth is being represented by one single DN number. The next immediate number is 230. If I want to reduce this size of the pixel and go for a lower or a higher resolution, or go for 1 by 1 meter or 2.5 meter by 2.5 meter size, I have this 200 and 170. This is getting transformed into 200, 170, 202. So the interpretation and the corresponding digital number has changed now because my resolution of the pixel has changed. This is how the digital array numbers are being played with. Image is a photographic documentation or a record of feature of the ground. Interpretation is defined as examining the photographic image for image and judging the significance. So what we have is image interpretation, enumeration, and the calculations related to or quantification or calculation. Next, how are these images being interpreted? What are the different elements? So if I look at the pyramid, the least easy to work with is the tone and color of the image. That is the primary element of an image. The secondary level, I have size, shape, and texture. Arrangements of the tone. Next, at the next level, what I have is pattern, height, shadow. That is the higher level of image interpretation. The most complex tertiary level, I have the sight and association of the images, like the length of the shadow of a tree at particular time when the image was taken. That is the association linked to the original object. The shadow is an association. So if I want to look at these higher complex level of data, then I the tertiary level of interpretation. Image interpretation is again accompanied with field observation. Like I said, 5 to 10% of field authentication or survey is essential. Then it is linked to the direct recognition, like interpretation judgment based on the adjacent sites by inference, probabilistic interpretation. Then it deterministic. So first we do the probabilistic interpretation. We do direct recognition, like when I have a stream, do I have anything crossing the roads nearby? Or if it is a straight line, then it should be a road. If it is a curve feature in the image, it should be a stream. Then I try to interpret it probably whether it is a natural forest next to the road or a field. Then the deterministic is rigorous and precise. Then I accompany it with the field observation also. Material is designed to meet the rapid and accurate identification. So we get back to the same numbers again. Interpretation is in terms of visual, which if it is a pictorial, visual is easy. Digital, this is what I was talking about. The digital number allotted to the radians measured by the each pixel for a particular sensor. That is the number which you see in a electronic form of image. These DNs range from 0 to 255 or 8-bit computer, 8-bit range, 9-bit range, and 2 power 8, something like. So these are all get into complexity. We'll not get into that level now. Next, at the end, the product information products that we use are, one is FCC, which you like. Just remember, when we get the images, they are either in TCC or FCC format. FCC is false color composite. TCC is true color composite. The rightmost satellite image is TCC. That is a true color. It's FCC because here it is showing the water bodies in black and vegetation in red. So it is a false color composite where we have only shades of red, green, blue. And introducing color to this one single band will sometimes generate these FCC images, like the bottom one. Once it was a set of black image, one single color image that was black was used. Then we have introduced color to this image, which has generated the same image in 3 colors, RGB. So application to civil engineers, this is more general. Okay, before I get into this, so these two true color composite and false color composite images are being enhanced and being given to multiple users. Their utilization purposes. Now, who are all these multiple users in our department? That is mainly for what we have. We can use this data for land use of the soil. That is a geotechnical engineers, soil characterization, land use, land cover, change detection, and all. Then the geologists who use in geomorphological mapping, groundwater exploration, environmental studies, drainage analysis, and to some extent the mineral exploration also. Then the third sector is the urban land use to detect the extent of urban enhancement. That is where infrastructural engineers come into picture. Then the hydrologists, water sources, they check the surface water bodies, extent, snow cloud discrimination, glacier, etc. Then the hydrologists, so watershed analysis, delineation of watersheds, characterization. I think we had a section on HECRES. So these engineers use this sector of the RS data, monitoring watershed development and river valley perds and all. Environmental respect to environmental management, pollution, impact assessment, extent of vegetation and water bodies being contaminated, other stuff. Then we have the traffic engineers, street network, vehicular routing, location, and land parcel zoning and divisional planners. So natural resource based floodplains, impact assessment, then facility managers use this RS data, locating for the underground pipes and cables. Disaster management is especially in case of events of earthquakes, floods, and droughts. Damage assessment, slope analysis, we do it. Then change reduction analysis also is possible with these data. So, for a example, we have this TM image and TM spot. So image of the same site with two different sensors. One is TM and another one is a spot sensor. So how clear it is, especially in this black zone, the artificial vegetation zone, that is clear. Clearly you can see the shades of the black and reds. Now the next one, last topic is GPS. Is unequal, the global positioning system of the satellites. Why we are using this now? Since we had been getting the RS data intermittently, then there was a development where it was decided to go for getting the information as a real time, getting the information as a real time. So somewhere reaching nearer to ideal RS. That is where we have developed this concept, the global positioning system. It gives accuracy and flexibility of positioning and GIS data capture. So what it has, the navigation, satellite timing, and radiation, this one, 3D positioning and 3D position of any object 24 hours a day we can get. What is advantage of that? Is advantage of the GPS. It has an accuracy up to 100 meters, and positioning of moving and stationary objects both can be captured. Static positioning, kinematic positioning, and reference. We get the data of all the three. How does it work? It has a set of 24 satellites, of which 4 of them are in one orbital plane. They'll be in one orbital plane. Their distance is fixed. The distance from the satellite is used as a reference. All the 4 of these satellites capture the same land, that is this plus mark, say same data. Now, like this, we have 6 sets of satellites each, 6 different orbital planes. That is, so total 6 orbital planes is Earth is divided into 6 orbital planes, each of 60-degree inclination at a latitude difference of again 60 degrees. So it's all playing with 6 orbital planes, 60-degree inclination, 60-degree longitude, with 4 satellites in each. That is how a GPS works. So data from 4 satellites is captured for the same place. Similarly, another set of 4 we will be looking at from different perspective, from different orbital planes, and accurate clocks are given in all of these. They need to know the satellite location also. These satellites correct for the ionosphere errors and remove the errors and then place it. Then there are 2 segments of this GPS functioning. So this is how it is. We have 4 sets capturing the same navigation, and the different 6 orbital planes are like this, as shown in this one right side figure. Navigation, which shows the 24 satellites which are being placed at different locations, orbiting around the Earth, and 60 different orbital planes revolve once in 12 hours at an altitude of 20,200 kilometers. These are known as artificial constellations. These four in one orbital plane are said to be in one artificial constellation. Observer on Earth can receive the signal from satellites at a time. The same 2D picture, standard positioning and pseudo positioning services are used. Then we have the differential GPS. So differential GPS, what happens? The basic concept of GPS had certain errors because of the clock and positioning, the timing of the satellite and other stuff. So these errors are being eliminated. Simultaneous measurements are made by a static station receiver by one or more this one. Base station receiver is located at a point. So base position, we know we have a remote corrected position. That is the added advantage of differential GPS. So base position, the data received from base position is being corrected by the second position, whose distance, link, association, everything is known, or everything is being computed scientifically. So that is the advantage of differential position. Now, absolute positions give real-time kinematic positions are there. The errors in GPS is because we need 4 times at any time. If any one satellite is non-functional, then the GPS would give an error. The data would be erroneous. Multipath and ionospheric delays, topographic other delays will be there. Effects of, see, a certain example of this error, especially if we have certain hindering objects like buildings or other reflective surfaces, the data received by the signal will be erroneous. That is, so we should have the receptor antenna and the satellite, and there should not be any interference between in this path. Applications of GPS is mapping, engineering applications, surveying, and then navigation, monitoring. These are almost the same as what all we have in RSS. All the usages of satellite is applicable for GPS also, with added advantage of real-time system being included. So we can have a live RSS in our mobiles. That is what GPS works for. So here, 1 minute. So there, I was explaining about remote sensing and different concepts of the remote GPS in our application mainly, especially in the civil engineering perspective. And so if I have time, probably I can show one live example of JS, one small, it's not an example, but it's a picture which shows about how we have used it for a remote place. So this is one of the sites in Zanzibar Island. So if you can Google it, you will know where this island actually is. It is on the east side of the Africa, a very small island. It has got all hilly regions. It is full of ghats, very small island, and you have a heavy, what I should say, a national highway passing through these hilly regions. It is similar to our Konkan highway. Now, one of the projects that we received was to estimate or to check the durability of this highway. It had got all landslides all along. The road was cut, and anywhere if you have any landslide in any on one of these positions, the whole traffic stop here, and you cannot reach any other place. And there was no way to come back also because it was all a single lane road. So the task assigned was to widen the road, make it a two-way in this heavy hilly region, makes unapproachable hilly region. So the only urbanization or only human living was in the initial phase of this road. After this, all these zones, it was all completely hilly with no human settlement. So anything had any obstruction is there, the person has to come back by walk or something, leave the vehicle there, come back to the settlement at the starting of the road, and then take some other help to make the road clear. So it was a very unapproachable location. Like the path was not that easy. Then what we have, my special application was in that was to assess the assess the influence of groundwater and surface water in this hilly region. The region received around like 4,000 to more than, it was more than Kerala rainfall. It was more than like around 4,000 to 6,000 mm of annual rainfall. So in that scenario, everything would landslide and the monsoon months are almost like 10 months over a year. So everything that falls, the whole rainfall would cause a landslide. The things would recede back to these roads and block it. And especially because of this continuous rainfall, the hills absorbed most of the water, and they started hills absorbed most of the water, and they started developing enhancing the groundwater also. So what we do is now we take this pictorial image. See, most of us cannot go to this site and look at the station marks are at every 100 meters. So traversing these 4 to 5 kilometers in a hilly zone, taking a vehicle and then looking at every 5 meters distance, what it is all about, that is almost, it's a tedious job. So that is why we have taken the help of this GIS. We take a Google image, plotted the terrain or plotted the road path of it, the stations or different stations of it, and in this Google image, I can see the controlling streams or the streams which are crisscrossing this road and creating the flood zone. At the same time, how is the hilly region? How high is the hill next to this? All this I can know. Now, what are the labels that I have marked is the depth to the groundwater that we have received. So till 3 meters, there was no water. Then what could be the possible water level that would increase because of the soil strata it has? So, and here we don't have any water till 3 meters. But when you pass up to say another 2 kilometers down the road, you have some water at 1 meter only. Again, you don't have some water at around like 3.5 kilometers stretch. So like that, we have analyzed, used this GIS data to develop, to solve this highway issue in a hilly terrain, which is completely island, and to some extent, these interior zones of highway has tribes who rarely allow any modern human to reach that site. So that is also one of the social constraint to go there physically and do the survey and then problem or solve them. So it is like some only localites of that place can reach, who does the contract for us or who does the construction work for us once we give the designs to them. So there is an intermediate team who interacts between those tribal community and the designers of the outside world. This was just an example to share like how RS helps us to reach the remote locations. Any questions?
Participants,
Participants, any questions? Please type your questions if you have any question. Okay, now I request Mrs. S.S. Dete to propose a vote of thanks. Madam, over to you.
okay. Thank you, Wagmare sir. Am I audible?
Yes,
Yes, ma'am.
Okay. Good afternoon, all. I, on behalf of our institute, take this opportunity to propose vote of thanks. I thank our today's speaker, Dr.B.Siva Soumya madam, to give very nice information about RS and GPS. Thank you, ma'am. Thank you very much. For next session, we will meet at 3 p.m. sharp.
thank you.